All right. Good morning, everybody. I'm glad to see that so many people have made it here already, including myself, although it's still quite early in the morning. I was guessing yesterday that Black Hat intentionally moved away the conference from the center so they make sure that speakers don't get wasted so much anymore. Okay, so my presentation will be about SSL validation checking. What we'll talk about in the presentation is it's a little close to the famous Apple bug, go to fail, and give you some ideas about the research that we did along with that topic. From this go to fail vulnerability, we developed an idea of how to test for SSL validation checks and actually also create a prototype that we, of course, applied to a bunch of different applications. So I'll also speak about the actual results that we achieved with our prototype. Quick bio about myself. I guess I'm mostly known for the work that I did so far in the industrial security world. I spent a decade with a large German industrial vendor, was heading their hack-proof products group and eventually also founder of their product cert. But for quite some time, I'm doing my own thing now, running a smaller security consulting company called Lime Security, also focusing on secure software development and industrial security in my first professional life. My second professional life, I'm a professor at a university back in Austria where I really like to teach classes like web and application security, botnets and honeypots, and penetration testing. Nonetheless, in both worlds, my research interests is industrial security and application robustness, which brings us back to this topic. So what was the background for the research? So I guess all of you who have an Apple device have read this security bulletin about the security content of iOS 706. If you go through it, it says something like there's a problem with data security. An attacker with privileged network position may capture or modify data in sessions protected by SSL TLS. So when I was reading this, I was thinking, oh boy, this is really already the worst case. And then it came even better. Secure transport failed to validate the authenticity of the connection. What did this mean? So if you're the end device, then you would not be able to actually tell if the validation of the SSL TLS connection had really happened properly. So in my opinion, this was really the worst case of the worst case, right? So the question was, what was wrong in Apple's SSL code at that point? So the actual vulnerability happened in the SSL keyexchange.c part, which is, of course, as you would guess, the official SSL TLS library that Apple uses. What happens in there is just the regular steps that you would expect to take place when it comes to SSL TLS connection setup. The function would process the client hello, of course, also the server hello, and at some point the certificate, and initiate the key exchange, especially for TLS connection where forward secrecy is involved. I want to spend a minute on forward secrecy. Why is forward secrecy a good thing? Why should everybody in this room love forward secrecy? If you haven't heard about it, please keep close attention. Perfect forward secrecy is really nice because if a bad guy breaks into your web server, or maybe a foreign agency which legally claims to be authorized to hack your server, gets the server key, they cannot decrypt traffic they have captured at some point in the past. Why? Because individual session keys have been announced. So that's why everybody, especially since 2013, should love forward secrecy. So the problem actually happened in a C function called SSL verify signed server key exchange. And if you look quite closely to the source code, even if you're not familiar with programming in C, you see two go-to fails in the middle of this. So it looks a little strange. What's the problem here? Obviously, the first fail is really correctly bound to an if statement, but the second wasn't. What does this mean from a program flow or logic perspective? So there's I think we can only guess what should have happened. So the code should have calculated several cryptographic checksums and then passed those on to a function called SSL raw verify for the actual verification process. If the SSL raw verify function succeeds, then the error value that we had up here should have been 0, which is quite commonly meaning no error. That's what the function uses to signal everything's good, proceed with the connection. The problem here really was that the very first go to fail that we saw, if that succeeded, this meant there has been a problem and the error is non-zero and the connection wouldn't continue, right? In C, of course, the second go to fail always happens if the first one doesn't. So the result was that the code jumped over the different calls, and in the end, the consequence was that the full SSL validation process didn't take place. So several checks just didn't go through. Ultimate consequence, so different ideas. So generally, the validation was not working properly. Maybe the link between the ephemeral key and the certificate chain was broken. It might have been possible to send a correct certificate chain to the client, but sign it with the wrong private key or not at all. Maybe also there would have been no proof that the server actually possesses the private key matching the public key in its certificate. But pretty straightforward. Users wouldn't have received any of those typical warning messages when there's forged certificates around, thereby making man-in-the-middle attacks probably easier. So we're really thinking, how is it possible that a critical security bug in a security function went unnoticed for quite a long time? Could it have been detected? Could it have been detected? Probably yes, if you have the source code. I mean, by using a source code scanner, I'm pretty convinced you could find this. I was even thinking if you could have just found it through looking at the compiler messages. So it's quite some time since I did a bunch of C coding, but I remember whenever I did something wrong with the coding and I created code that had some errors in the logical branches and the conditional statements, which would end up in some code that was never jumped to, the compiler would issue at least a warning message. So with the source code, probably this could have been detected earlier. If the source code was not available, maybe. So our research question, and that was actually, so go to fail was really the starting point, was to which degree can SSL validation checks of third-party apps be systematically assessed if the source code is not available? And if you're able to do an assessment like this, of course, what is the overall state of SSL validation checks, especially when it comes to mobile apps? So the question we are asking was, are doing mobile application developers the right things? Are they doing their homework correctly when they include SSL function because they have to transport confidential data? Are they using it the right way? And this led to our SSL validation fuzzer concept and architecture. What did we want to do? Again, come up with a methodology which allows us to test whether SSL validation checks are done properly in mobile applications without the source code. From that concept, of course, create a tool which helps us to automate certain steps to test quite a number of apps easily. And we're also thinking, okay, once we have this tool set up, what might be good candidates for testing our tool? And of course, we thought in the first place about e-banking and mobile apps. Why? Because at least in my home country, in Austria, there has been a huge run on promoting mobile banking from your smartphone on the one hand, and on the other hand, we just thought the financial sector has quite high confidentiality requirements and data security requirements, so those guys should really do their homework properly. And finally, we wanted also to check the same application on the 3 different major mobile platforms, Windows Phone, iOS, and Apple, and see if there's maybe different patterns. So what were the main assessment components? The main assessment components on the client side were just regular mobile equipment, like Samsung Galaxy S2 running Android 4.1.2, an Apple iPhone 5, and a Nokia Lumia running Windows Phone. on the software side, we had a modified version of MITM proxy. Those of you who are already into penetration testing know this software. It's a really, really good piece of software for doing man-in-the-middle attacks. It's an open source software that we modified to interface to our SSL validation fuzzer. And finally, of course, the fuzzing component as such. What I'd like to point out at this point is what we're not doing is fuzzing the SSL library. So we're not fuzzing OpenSSL, Start SSL, whatever. There's other companies and groups doing research like this. What we wanted to test and assess was really the validation component. So really, is the software developer using the SSL library in the right way? What was the setup and architecture of our component? So on the right side, we had our poor clients, Android, Windows, and iPhone. They were connected through a regular wireless network to our evil proxy. The most important software components here were IP tables, DNS mask, MITM proxy, a certificate authority, because we had our own certificate authority for some test cases, and our SSL certificate fuzzer. And finally, of course, a connection outwards to the internet, because, again, we wanted to get into the middle of the connection. Why did we have this setup? Well, we started out differently. We started out by just entering a proxy configuration into the mobile device, and thereby trying to force the mobile app to talk over our proxy. The funny thing was, some of the mobile banking applications complained. So they said, hey, I detect that you have a proxy configuration. There's a hidden security risks. I will not work. So I found this interesting. Does this add some security? Probably not. So what did we do? Just move the proxy configuration out on the network, do the redirect to our proxy on the network side through IP tables, and then, of course, the applications didn't complain anymore. Okay, what was the testing approach? So what we wanted to do really is more target-oriented fuzzing of the SSL validation component. So the process was that our application would really try to connect out to the internet and try to reach out to the server. And from the server, of course, we would pull the initial server certificate through our man-in-the-middle proxy, pass it on to our fuzzing component, and generate a bunch of new certificates which are somewhat close to the original certificate. That's also for some of the test cases, that's the reason why we needed our own certificate authority. So the idea was really to think about how might a software developer have checked for the presence of the right SSL certificate. So test cases. We had to think about test cases, but which ones actually do make sense? So we also thought, how twisted can a developer's mind be? What could he check for from an SSL certificate perspective? So maybe we thought maybe some developer really checks hard-coded the certificate serial number. Actually, we found that's really true. But the majority of our test cases really is just based on the regular X509 standard certificate fields. So something like host name, the validity dates, invalid not after, invalid not before. So our original first test case was case number 2, a valid certificate. What do I mean by this? This was a certificate that we generated with our own CA, which was marked trusted on the device, but had really nothing to do with the original certificate. What did we want to check by this? We also wanted to check how widespread certificate pinning is used already. So I think certificate pinning is quite an interesting approach, and we thought maybe for this application field it's a good thing. At some point we had a misconfiguration, and we ended up with our proxy just sending some random certificate, which was not marked trusted, which has just some snake oil information in there. And actually some applications, some mobile banking apps really accepted the certificate. So we wouldn't have started with this test case in the beginning, but it really worked out, so we kept the test case, right? So beside the regular test cases that you derived just from the X509 standard certificate fields, we also found it worthwhile to look not only for certificate pinning, but also for SSL stripping. SSL stripping, to make a long story short, is really a way of being able to preventing an encryption taking place. So think about the banking application trying to connect to a server, maybe starting up with regular HTTP traffic, and then trying to create a SSL connection by reaching out to a resource that is HTTPS protected. If you are an attacker in the middle of this connection, and the implementation is done the wrong way, you are able to redirect this request for an encrypted resource just to another website, which is maybe a very good phishing site, and therefore preventing the actual secured connection from ever taking place. And this is also something that unfortunately some banking apps are vulnerable to. So I have a short video. I hope it works. So we have an application on the right side. I didn't want to show the actual banking logo. What did we inject here? The very evil Lime Security company logo. So we were, of course, able to get into the connection, but it's just HTTP. Now our user clicks onto the mobile banking, an encrypted connection should take place. This is very, very close resembled to the original website. Again, for demo purposes, we put intentionally our company logo there. And on the lower side of the screen, you see, of course, already the login information, the PIN, the TAN, whatever is needed by the user to log onto the website. And then, of course, we just redirect to the regular banking application. So this is, by the way, an Austrian bank, but those guys have luckily already started to fix this. So the funny thing was that we just started by looking at the regular certificate fields, but over time we found other test cases like SSL stripping, which are really not related to the X509 standard, but we also found really, really worthwhile to talk about and to include in our research. So what about the results? Until beginning of August, we had something like 90 applications tested. So we started out with national Austrian banks, moved over to Germany, and then went to China, to India, US banks. So it was overall 90 applications that we tested. The bad news about the results, so probably the bad news for you, I know everybody loves vulnerabilities, but we have made agreements with the banks that those who have not fixed them, and there's quite a bunch of them, we won't name anybody, not on the positive side and not on the negative side. But still I was surprised, even in 2014, there are still several apps, both of European and international banks, regardless of the company size, that do not apply any validation checking to their SSL connection and are therefore really susceptible to just the default man-in-the-middle attacks from, let's say, around 2000. So this is what I would consider a total fail, at least in the financial industry. We also found, of course, several lower degrees of validation. So some apps were, as I said, susceptible to SSL stripping, also making man-in-the-middle attacks easier for phishing purposes, for example. We also looked how widely deployed HSDS is, so HTTP strict transport security. Some of you may know it from browsers, of course. It's not as widely used as I expected. Also talking about poodles, the Poodle vulnerability, which came around just this week. We did a very quick test just 2 days ago. How many of the server-side counterparts of our banking applications would be configured to talk SSL version 3 in the problematic CBC mode? Yes, there was quite a bunch of them. So of the 30 we tested, I think at least 15 were talking SSL version 3 in CBC. And I think in this case, this could be prevented. Why? I think the people reluctant to change from SSL version 3 are reluctant only because of legacy clients, like Internet Explorer 6. This is not the case here. Why? Because you do have the client under your control. You're the bank rolling out or handing out the client to the mobile users, so you do not have to worry about any ancient browser, right? We also found some interesting results. Some applications used out-of-band TCP connections for whatever reasons, not only SSL, so also plain text out-of-band TCP connections beside the SSL connection. Some apps transmitted quite a bunch of device data, which maybe raises privacy concerns. So I have one example from the PayPal app. I think that's a legitimate purpose, but I still found it interesting to see something like the device identifier, the SIM serial number, the subscriber ID, the geolocation different, so if it's jailbreaked or not. But I wasn't aware what kind of data is being sent from the mobile. So that's why I think the purpose is really fraud detection or risk detection. That's why data like this is being sent. But nonetheless, I think it's really worthwhile from time to time to peek into the data that is being sent from your applications out to the internet. The good news, well, luckily several banking payment apps exist which do apply all SSL validation checks as you would expect, so really state-of-the-art, homework probably done, even certificate pinning in place. As I said on the next line, in some cases you do find certificate pinning. When talking to banks, it was most of the time more on the Android side. Why? Because on the Android side, those guys have had issues already with banking Trojans doing exactly the same thing as we have been doing, bringing their own certificate authority with them, installing into the device storage, and then being able to tap into the mobile connections. Also, if the developers use the provided validation functions, the platform-provided validation functions, the results look much, much more better than if homegrown crypto and validation functions are used. So not a big surprise, same here. So what should you take away from this talk? Assessing SSL validation checks of a third-party app is possible, I think, to a good degree, even without the source code. I think that's very important to do so because it's quite common to procure, to buy third-party applications from somewhere else, and you really want to know if the protective measures in there are working or not. Even in 2014, in the banking sector, SSL validation checking is not properly done in all cases, and probably the bad guys have also figured out where it's worthwhile locally to exploit this. So we also saw some local areas where we found the banking applications to be more insecure than others. And in the end, of course, it's up to the developers who create those applications. Those guys need to be educated how SSL and validation checks really should be used in order to prevent something like the next go-to-fail, at least for widely used apps. So with that, I'm really already at the end of my presentation. Thanks to some colleagues from my university and my company. More information is available at this link, and I'll be happy to take any questions. Thank you. It's difficult to see questions. I'm nearly blinded. Yes? So I would say it's different. It's difficult because we had test runs. So I think at least 20% failed at one of our test cases overall. So not only the first test run, which was more nationally, but also internationally. So roughly maybe 20%. Any other questions? Yes? Sorry, could you shout out to me? Yes. So how can you perform any additional tests? So we will make this tool available. So if you are an app developer, please approach us and you can get this tool. We just do not want to put it yet fully on the internet. We had this request by banks. So if you identify yourself to us, and we'll make sure we try to find out if you're a bad phishing guy, then probably you won't get it. But if you look somewhat legitimate, we will pass this tool happily on to you so you can use it for your own application development, or even if you procure it from the outside, that's one way of doing it. Any other questions? Okay, thank you very much.